Welcome back. We just saw how to use the chain rule. Even in longer chains, those chains can go as long as we want. You can keep composing functions with each other indefinitely. So on this video, I thought we would incorporate it into some other things, including a more complicated example, as well as see if we can use it to find out some derivatives of functions we didn't know yet. So first off, let's try this next example. You'll notice it's not just a chain rule, that this is going to be a chain and a product rule. We really could just take this to the fourth, take this and cube it, and then multiply all of those together in a very long, tedious way that I probably could not do without making mistakes. Or we could recognize that we can do it as is, first using the product rule and then the chain rule. So let's use this product rule to our advantage here. We're going to have the derivative of the first, whatever that is, leave the second alone, plus we're going to leave the first alone, and take the derivative of the second. So let's go ahead and take those derivatives now. My chain rule for the first one says bring the 4 down, leave that inside as it is, then take the derivative of the inside. The derivative of the inside is just 2 plus, I guess, 0. Cool. That's it. My derivative of the second says, okay, bring the 3 down. Oh, I lost this 3. Sorry about that. When I bring the 4 down, I need a 3 up there. Bring the 3 down, get a something squared, leave the inside alone, and now take the derivative of the inside. And parentheses are not just like nice here, they are necessary, because otherwise what you're going to write is going to be wrong. We need this entire polynomial to multiply this next entire polynomial, 3x squared minus 2x, and then minus a 0. All right, and as always, if this is your final answer, go ahead and leave it like that. I really wouldn't want to try to multiply this out, so I'm just going to leave it just like that. Great, not so bad. What it takes is comfort in trusting the process, knowing which step to do when, and probably nice use of brackets and parentheses can really help with that too. All right, that was it, the product and the chain rule together. Of course, we could have done any mix of the quotient, the product, the chain rule, any other derivatives that we want. Next up, turns out when we learn entirely new techniques, we win prizes. We know the derivative of e to the x, but we don't actually know the derivative of 2 to the x or 10 to the x or any other exponential yet. To get this, we are going to need to remember something. We are going to need to remember our exponentials. So I'm going to do a little side work over here. Remember that if I write natural log of e to the x, that natural log and that e to the x cancel. In fact, you might even remember that there is a power rule that says that this x, any exponent inside of a log, comes out front. So this would be x natural log of e, and natural log of e is just 1, so this is just x. Point being, these are inverses. Natural log and e to the x are inverses. They should undo each other, so you should just get an x out. If it's an inverse, it should work both ways, so e to the, and then I compose that with an inner function of natural log of x. This should just be x. Okay, so how do I use this to help ourselves? We are going to take this b to the x over here, some base, I don't even know what it is, and I'm going to rewrite it as e to the natural log of b to the x. Why? Well, because I'm allowed to. E to the natural log of b to the x should just be b to the x. Okay. But now I can go one step further. Remember that I have an exponent inside of a log, and so I can bring that exponent out front. This becomes e to the x times natural log of b. Ta-da! Not super impressive right now, I know. But rewriting it this way is really handy, because now what looked like b to the x looks a lot like e to the stuff, and then with that stuff is some inner function. What does that tell us? If I have e to the x times natural log of b, then I should be able to take a derivative and say this is going to be e to the natural log of b, that's a constant, times x. I didn't change anything there. I just rewrote the order. And my chain rule, as I take this derivative, my chain rule says, now take the derivative of the inside. What is the derivative of natural log of b times x? Natural log of b looks scary, but it's just a constant. And so this becomes just natural log of b. A constant times x, if I take its derivative, I just get the constant. So that's all I really have here. All right, neat. It doesn't look that pretty, but this really is just our chain rule in action. We rewrote it in a way that my chain rule could work. Let's go ahead and take a look here at this fun bit. This looks familiar. This is the same thing as what I started with here. And so if I change that back, we decided that this was just b to the x rewritten. This is just b to the x. So I clean that up. Lo and behold, what do I get? I get natural log of b times b to the x. That's my derivative. Thanks, chain rule and log rules. Let's just make sure this makes sense real quick. I'm going to do a little bit more scratch work on the side here. So if I try to use this rule with e to the x, if I said, all right, I have e to the x and I try to take its derivative, I would say this is natural log of e times e to the x, according to that formula. But natural log of e is just 1, so this is e to the x, and it actually agrees. Okay, let's do a couple of extra practices. You might actually even recall that when we did the proof of the derivative of e to the x, we said it should be, for any exponential function, for anything like b to the x, we should get something that looks like b to the x times a constant. Way back when we did that proof. And we weren't sure what the constant was. We defined the number e so that the constant would be 1. E was the number that makes it so that this becomes a 1. We just weren't sure what to do with other bases. Like, what constant should we be multiplying it? And this is the constant, natural log of b, whatever that base is. Super neat. Also, another reason why natural logs and e's are really important. You might have seen totally mysterious before this point, but they are intrinsic to how calculus works. All right, let's do a couple of examples. d dx of 2 to the x should go pretty fast. This is just natural log of 2 times 2 to the x. That natural log of 2 is a constant, so it's a constant times my original function, 2 to the x. Let's do a bigger one, e to the secant of theta. If I take that derivative, well, this looks like a chain rule kind of problem here. I have an inner function and an outer function. My outer function is 3 to the stuff, so I get natural log of 3 times 3 to the stuff. And now I need to apply this chain rule and see that I get the derivative of secant. Do I remember what that is? Secant of theta times tangent of theta. Great. That's it. One nice product thanks to that beautiful chain rule there. All right, one last one. Let's do a nice long triple chain here. Let's take its derivative. This is going to be derivative of tangent, secant squared. Leave everything on the inside alone. One, two, 3 parentheses. Great. Next chunk. Looks like I'm on to the cosine sine part. So I'm going to take the derivative of cosine is negative sine. Notice those parentheses are now really important because otherwise it would look like a subtraction. Sine, negative sine of x. Great. Moving on to the next part. the derivative of sine is just cosine. Okay, a totally ridiculous function that I've never seen show up in life, but it's a nice practice for these chain rules. I wanted to just end with a note. The chain rule is important, it's magical, it's already bought us a new kind of derivative, it's going to show up in implicit differentiation and related rates and all kinds of multivariate stuff, but it is also confusing, but a special kind of confusing, and I wanted to warn you about this. For whatever reason, a lot of students, it doesn't make sense, and then it clicks. And then once they get it, and then they do it a couple times, and then they let it click in there, it just makes sense, and they can do it very, very fast. And so you need to give yourself the time and the space to think and work through it at your own pace until eventually you kind of catch on to the pattern and the understanding of why it works and how it works. And there's really no way around it, unfortunately, that I've learned. So you'll get there if you just keep trying. I believe in you. You can do it. Until next time.